So, welcome back to this advanced manufacturing and process modeling course. So we have been discussing several topics since a length of time now. So we are at present discussing the process modeling concepts of casting processes. So till the last class I have discussed about the flow chart that is followed, sequence of solution for different governing equations in case of density and pressure based solvers. So there are another very key important aspects of fluid flow, heat and mass transfer aspects to achieve solution of these governing equations in case when it is applicable to casting solidification processes. So these the important another important segment like the solution algorithm is the boundary and initial condition of the flow physics. So today we will start with that. So how to define boundary conditions? So to define a problem that results in a unique solution, one must specify information on the dependent flow variables at the domain boundaries. So such as specifying the flux of mass, momentum, energy, etc. into the domain, and also defining boundary condition involves the identifying the location of the boundary, that is where is your inlet, flow inlet, where are the wall, where and which which locations are can be defined by the symmetry boundary condition. So so supplying these informations and also supplying the values of the variable at the boundaries. So the data required at a boundary depends upon the boundary condition type and the physical models that those are employed to solve the flow and the heat and mass transfer problem that is in hand. So one must be aware of the information required for the boundary condition and locate the boundaries where the information on the flow variables are known or can be reasonably approximated. Poorly defined boundary conditions can give a significant impact to the solution and it can bring out erroneous results. So we need to be very careful about defining the boundary and the initial conditions to solve the flow physics and also the analogous heat and mass transfer problems. Okay. So so the available boundary condition that are generally employed for. So again the example is taken here for a classical fluid flow heat and mass transfer solver that is implemented in a commercial package Fluent. So I am taking this example because most of the students can get a hands on this Fluent software and they can try out to solve the problems in the domain of casting solidification. So let us start with the available boundary condition types that are available in Fluent. So in case of external phases the boundary conditions available are pressure inlet, pressure outlet, and for incompressible fluid the available boundary conditions at the inlet and also at the exit are velocity inlet and outflow. Whereas in case of compressible fluid the inlet boundary condition is mass flow inlet and pressure far field and mass flow outlet is at the exit. And the other boundary conditions to describe the flow physics and the also which is applicable in case of phase transformation like liquid to solid transformation, that is the core intrinsic to the casting solidification processes are are wall, symmetry, axis as well as periodic boundary condition. And there are some special boundary conditions available to describe the flow pattern and flow physics like inlet vent, outlet vent, intake fan and also exhaust fan. So let us start with the pressure inlet. So pressure inlet boundary condition specifies the static pressure at the inlet typically used for compressible flow simulations. And number 2 is periodic boundaries, which is often used to depict that the model has a repeating flow patterns, reducing computational effort by simulating only a small section of the domain. So this is a very critical boundary condition that is widely utilized in case of solving the flow physics and even in case of phase transformation problems. So, because often it becomes computationally expensive to solve the problem, for the entire scale of the problem, for the entire dimension of the problem, rather it can be effectively solved for a small domain within the considering the domain within the larger domain of the casting solidification problem in hand, and thereby we can basically estimate the the pressure, velocity, and also the volume fraction, that is of the volume fraction of the secondary phase that is evolving from the primary phase, and what will be the viscosity in the due to the solidification that is achieving. So, all those things, and also that there is a great extent of application of periodic boundaries when we will when we try to simulate the microstructure evolution in the casting which is undergoing solidification. So, we will discuss about microstructure modeling a little later. So, for now the periodic boundary we are discussing, which is applicable to solve the flow physics, that is like a domain where repeating flow patterns are available. Like so you can see the example of periodic boundary condition is shown over here in case of a 2D tube heat exchanger. So, you can see that there are these arrows shows that there are translationally periodic planes, so between 1, 2 and 3. So, out of that maybe any one of the location can be solved, and maybe only this much section can be solved, and then it can be useful to approximate the situation for the entire domain in hand. Okay. So, now next is wall boundaries. So, wall boundary is basically it defines the solid surfaces where no slip conditions are enforced in viscous flows affecting velocity and thermal properties. So, what is no slip boundary condition? So, no slip boundary condition says that at wall the velocity is equal to 0. So, assume that there is a fluid which is flowing between two parallel plates. So, these are the two parallel plates. So, then the velocity distribution takes the form like this. So, if I draw it here, yeah. So, it is basically attains maxima at the center of the both the surfaces, and also it is the velocity is 0 at the wall. So, this is basically, so V is equal to 0 at wall is the no slip boundary condition. Okay. So, yeah. So, this is so after no slip boundary condition, we will move to the next boundary condition, that is symmetry boundary. So, it is the boundary condition which is used to reduce computational effort significantly by enforcing 0 normal velocity and 0 normal gradients of all variables across a particular boundary. We will also demonstrate the example of a symmetry boundary later on while moving with this class. So, so the next in the line is mass flow inlet. So, like we discussed at the top, so mass flow inlet is applicable for compressible fluids. So, it specifies the mass flow rate at the inlet, commonly used when the inlet velocity is unknown. Okay. So, otherwise the velocity inlet boundary condition is used, and then is next is the pressure outlet. So, it defines the static pressure at the exit of the domain, allowing flow adjustments based on upstream conditions. Okay. So, a example of you can see that so here this is a example. So, here it is a velocity outlet that is given over here, but it can also be described as pressure outlet. In that case, the velocity at the exit of the domain, flow domain, will be automatically adjusted based on the specified pressure at the upstream location, that means at the boundary, at the exit boundary. And then the final is the outflow boundary condition. So, it assumes a fully developed flow at the exit, which means that no additional gradients in flow properties are applied. Okay. So, with this we are moving to a case study, which is a which is taken from our published work. You can refer this paper to gain in-depth information about the work. So, this is a typical I mean solidification transport phenomena which is solved using I mean multi-phase flow model, Eulerian multi-phase flow model, like we have discussed earlier also. So, it works on the principle of I mean volume averaging technique, I mean so Eulerian multi-phase flow model. Okay. So, I mean so it works based on the principles of I mean volume averaging technique, where I mean each of the phases share the same pressure field, and also I mean they act like a interpenetrating continua. So, this is the basic concept in case of Eulerian multi-phase flow model. So, in this case you can see so this schematic shows you the boundary conditions applied at different surfaces. So, this is a practical example how the boundary and initial condition play their role in case of determining the flow physics and also the heat and mass transfer conditions that is happening within the computational domain in under consideration. So, here you can see that there is a velocity inlet boundary condition is specified with a velocity magnitude of 1.24 meter per second. Of course, this is a case of incompressible fluid. So, that is why velocity inlet is considered here. Okay. So, I mean so that means as we know that incompressible fluid, the density does not depends on pressure. So, density remains pressure independent. So, a velocity inlet boundary condition is specified at the top of the. So, this is a typical example of cooling slope. So, this device is basically useful for I mean semi-solid slurry generation prior to solidification of the I mean melt. So, I mean what is the basic purpose of the this tilted I mean flow plane or hemispherical domain. So, I mean so basically it exerts shear stress to the liquid which is flowing along the wall, and then because of the applied shear stress it is basically I mean fragments the evolving dendrites and they and then they fragments, and then it results in I mean near spherical grains within the which remain suspended into the flowing liquid, and then I mean so which promotes to the globularization of the microstructural features, and that benefit is derived into the I mean solidified components. So, we have discussed in detail in the casting module of this course. So, you can revisit that to understand it the mechanism of I mean near spherical grain formation better. Okay. So, after the velocity inlet boundary condition I mean so it is specified at the top of the slope where the superheated liquid melt is poured into the slope. So, superheated means it is beyond the I mean the liquidus temperature of that particular alloy. So, if I take an example of a typical aluminum 7 silicon alloy. So, in this case the liquidus temperature is roughly around 615 degrees centigrade. So, this is the TL of this particular alloy. So, I mean it must be poured in a significant amount of superheated condition. So that there I mean it should undergo I mean partial solidification while flowing along the slope for which the mechanism I have already explained to you. So, typical pouring temperature say for example, you can consider as say 645 degrees centigrade. Okay. So, I mean so we have evidence that there is approx 60 degree temperature drop that happens when we have allowed the superheated melt into to flow down the slope. Okay. So, I mean so here this is the concept of superheated melt pouring into the slope, and then moving ahead this the thin wall boundary condition that is specified at the bottom surface. So, this is the bottom wall. So, where I mean along which the liquid melt is flowing and then partial solidification it is undergoing, and that results in formation of near spherical or fragmented I mean primary alpha grains. So, in this case for the alloy I discussed above, it will be alpha aluminum grains. Okay. So, I mean so then so this is basically the thin wall boundary condition. Of course, no slip boundary, that means at the wall the u I mean x velocity, v y velocity, w z velocity is equal to 0. So, thin wall boundary condition and also no slip boundary, what does it mean? We have discussed in the previous slide, and here also we can specify the temperature at the wall. So, which is specified here as 333 K, which boils down to approx 60 degrees centigrade. Okay. So, so it is converted to Kelvin. So, you need to add the degree centigrade value with 273 K, because 0 degree centigrade is equal to 273 Kelvin. Okay. So, so this is the thin wall boundary condition. The bottom surface of the slope is specified, whereas symmetry boundary condition is specified at the top surface. So, you can see over here. So, this is the symmetry boundary condition. So, here basically the the scalar, the important variables that are getting solved into this computational domain. So, their value does not change across this wall, and also the normal velocity is 0, like I have discussed with you in the previous slide. So, this is the case of symmetry boundary condition. So, it is basically applied to reduce computational effort by enforcing 0 normal velocity and 0 normal gradients of all variables. So, here all the flow variables which are computed within this domain, so their gradients, normal gradients are 0 across this boundary. So, this is the symmetry boundary is specified, and then no slip boundary condition specified at the bottom of the slope we have already discussed, and outflow boundary condition is considered at the slope exit. Okay. So, what is the typical slope exit over here? So, here you can see, so these are the slope exit. Okay. However, here there is no mass flux of the partially solidifying liquid melt is going out from this boundary. Okay, because it is mostly because it is a hemispherical surface. So, it is mostly due to gravity and also due to surface tension, it is localized within a certain width, that is what I have drawn over here. Okay. So, this is the melt flow front. So, it is exiting the slope, and it is getting transported into a isothermal collector or isothermal holding component, you can say, container, you can say. Okay. So, then these are the locations where basically no fluid is going out, except the air which is defining a interface. So, because it is being done in a in under ambient condition. So, of course, there is a protective inert gas cover that has been considered over here to displace the air and to avoid the oxide formation with the flowing aluminum melt. Okay. So, here outflow boundary condition is considered at the slope exit, and adiabatic impermeable wall boundary condition. So, adiabatic impermeable wall boundary condition is given to the container walls. So, why it is adiabatic impermeable wall boundary condition is given in this container? Because here the objective is to store the generated partially solidified melt, which is called SSM slurry, semi solid slurry, in the state of semi solid slurry, semi solid state, so that it can be utilized for further processing for product development. So, the goal here is to store it in semi solid condition. So, we cannot allow it to cool down further. So, it should be kept at the temperature it is getting exiting the slope. Okay. So, that means, so T exit T E is equal to T container T C, I can say. So, to achieve this condition, so that is why this wall boundary of the container is specified as adiabatic impermeable wall. Okay. So, where the slurry is getting collected after flowing down the slope, and air exposure is considered at the top. So, you can also understand it as inert gases that is floating at the top of the flowing melt, which is undergoing partial solidification. So, the locations of boundary conditions mentioned above are indicated in the computational domain. So, it is shown over here, and the thermophysical properties of the alloy under consideration can be observed from this publication that is cited here. So, from our group. So, as these are some representative result of the flow physics and also the solidification morphology. So, it is basically a solidification transport phenomena that is solved during semi solid slurry generation. So, you can see that while the melt is flowing down the slope, it is, as I told in the previous slide, that it is undergoing partial solidification. So, that means alpha aluminum grains are increasing in number and also in volume fraction is increasing within the flowing melt, while it is travelling to the downstream direction to the slope exit. So, then because of the increasing alpha aluminum grains within the solidifying melt, so that it is getting converted to semi solid slurry, it is rejecting the solutal silicon, because we already told in the previous slide that we have taken the example of a aluminum 7 silicon binary alloy. So, here aluminum is the solvent and silicon is the solute. So, because the diffusion, solubility of silicon in alpha aluminum is very less. So, that is why it rejects soluble silicon, and that is also validated over here with these XRD plots, which shows that. So, you can see that these peaks are increasing while it is travelling from the start location, that is at the top location. So, this is start location of the slope or the melt flow front. This is the middle location of the melt flow front along the slope, and this is the exit location of the flow front along the slope. So, you can see the increasing peak height signifies the increasing solutal segregation, solute rejection, while it is travelling to the exit of the slope. Okay. So, this is, so you can see that this so here the solidification physics of the melt, which while it is flowing along the slope, is simulated with accuracy, and so these are the benefits of process model development. So, you can get a clear idea about how the solidification is happening when we are talking about casting alone, and also how the segregation profile, solute segregation is happening while the melt is here in this case when it is flowing, because that decides the morphology of the generated semi solid slurry, and when it will finally solidify in the form of a component, it will so this segregation phenomena also decides on the mechanical properties of the solidified part. So, this is just an example. There are several flow variables and also the solidification variables that has been solved using the Eulerian multi-phase flow model that has been developed. And so, the another example capability of the developed Eulerian multi-phase flow model shows its capability on predicting the microstructural information. So, you can see that it can predict the grain diameter of alpha aluminum grains. So, you can see that why we are calling it basically multi-phase, because it can simultaneously, the governing equations are getting solved for the solid alpha aluminum grains and also the parent liquid. Okay. So, the phase change process is perfectly simulated and individual governing equations are solved for individual phases. So, that is why we are calling it as a multi-phase flow model, and why we were calling it as multi-scale model, because it is solving the flow physics, solidification physics at macro scale, and as well as microscopic phenomena it is giving the output. So, this is the so it is that code that has been developed by us. So, so you can understand from here that you can basically couple the macroscopic model with the appropriate code, so that you can also predict the microscopic information. So, as the example is showing, so this the multi-phase flow process model of the casting process can perfectly predict the grain size distribution within the solidifying melt. Okay. So, this is a pop-up window, it shows basically the distribution of the grain size of the alpha aluminum grains at the slope exit. Okay. Slope exit condition of the partially solidified melt or SSM slurry, whatever you may call. Okay. And these are the analogous experimental validation which confirms accuracy of the developed model. Okay. So, you can understand. So, this is a real life example how you can employ the process models to understand develop a deeper understanding into the process. Like I told at the beginning that the importance of process model development lies in two fronts. Number one, it gives you insight into the physics of the process, which is otherwise extremely difficult to understand by the experimentation alone, and also it requires, if you try to do it by experimentation, it requires significant tooling, time, energy and cost considerations. And apart from the understanding process physics, it also allows to to be implemented as a process control tool, wherefrom you can basically gain a control over the process and also gain a control over the output characteristics that the particular process can yield while you are applying it to casting of a component. You can basically predict the microstructural information along with the flow physics of the solidifying melt within the component cavity, and also you can predict the temperature distribution, so on and so forth, which can give you an idea about the mechanical properties of the component upon solidification. Moreover, you can also use the output characteristics of this process model, that is computational fluid dynamics based process model, as an input to the mesoscopic models, where you can predict the microstructure, and then again the output of the microstructure evolution model you can use to predict the mechanical properties. So, you can basically virtually simulate the from scratch, from the first principle to the property at the component scale. So, that is the benefit of developing accurate process models in the field of manufacturing, where the example is given in the case of casting. Okay. Thank you.